Okay, let's talk about ring theory. And ring theory is part of mathematics that we will use in many fields that you see here on your screen: cryptography, coding, particle physics, graphic design, circuits, and telecommunications all use this idea of rings. And so they're just really providing us with a structure, a number structure that will allow us to do algebra. So let's start with a definition of a ring. So a ring is simply a set. And this set has two binary operations, addition and multiplication, which obey the following properties. We have closure of addition and multiplication, associativity of addition and multiplication, the idea of an identity element, 0, a multiplicative identity, 1. We have commutativity of addition. However, commutativity of multiplication is not a requirement for a ring. We have additive inverses, not necessarily multiplicative inverses. And we have right and left distributive law. Now, at times we'll find a set that obeys these properties, except it might be missing the multiplicative identity 1. So we call this a ring without unity, or RNG, which is missing the I for identity. So that's kind of a clever notation for a ring without unity. Now, if we add the multiplicative commutativity law, then we will call it a commutative ring. Here are some examples of some common rings that we will encounter. Here we have the integers, the rational numbers, real numbers, complex numbers, modular numbers, quaternions, also square matrices that have entries in these sets, as well as polynomials with those coefficients. So these are just a few examples that we'll see here in our discussion. This talk will be broken into 4 main parts. We're going to look at a few terms. We're going to look at creating new rings. We're going to see some ring functions, and finally ring classes. So let's start with just a few terms that we'll need to guide us. We're going to talk about the idea of ideal, a principal ideal, and also a zero divisor. The ideal is simply a subset of a given ring that satisfies 3 properties. This set is going to be closed under addition. It's going to be closed under multiplication by elements in R, and that's a little tricky, so let's talk about that for a second. If we have this subset J of our ring, any element in J multiplied with any element in the ring R should produce another element in J. So that's what we mean by closed under multiplication by elements in R. And then finally, our subset J should be closed under additive inverse. So every element of J has, in essence, an additive opposite in J. If these 3 properties are satisfied, we have an ideal of R. I have an example. I said earlier that the set of integers Z is a ring. A subset of that would be the even integers 2 times Z. If we add 2 even integers, we get another even integer. So we can say that 2Z is closed under addition. If we multiply an element of 2Z, or an even integer, times any other integer in Z, we will get another even integer. So we can say that 2Z is closed under multiplication by elements in Z. And finally, every even integer has an additive inverse that also happens to be an even integer. So 2z satisfies these properties, so we can say that the even integers 2z is an ideal of the integers. However, it is missing the identity, so we would have to say that it is a ring without multiplicative identity. So it's missing unity. A principal ideal is obviously a type of ideal that is generated by a single element in our ring R. In other words, R times A, where every element in R is multiplied by a single element. Now, it turns out 2z is also a principal ideal. We can generate the set of even integers by just multiplying every integer by 2. And so that's what we mean by generated by a single element. At this point, it would be appropriate to talk about an ideal that is not a principal ideal. So I have an example of an ideal that's not principal. So consider the set of polynomials that have integer coefficients. So we notate that z square brackets n. And I have a subset J, which consists of 2 times a polynomial plus x times a different polynomial, or where the two polynomials are in z square brackets x. So clearly this is a polynomial. It will also have integer coefficients, so it is an element in z. If we take 2 of these and add them together, we would get another polynomial of this form. So J is closed under addition. If we were to multiply one of these elements by another polynomial in z of x, we would get something similar in this form. So it would also be in J. And then finally, we could simply multiply this by a -1, which would also be a polynomial in z of x, and we would get the additive inverse. The point being that J will satisfy all 3 of those properties of an ideal. However, it's clearly not generated by a single element in our set. So it is still an ideal. It's just not a principal ideal. And the final term that we're going to talk about before we move forward is the idea of a zero divisor. And we learn in high school algebra that if you multiply 2 numbers together and you get the product is 0, that must mean that one of those numbers was 0. That's the only way you can multiply 2 numbers and get 0 in many number systems. However, that's not entirely true in every set. Let's look at, for example, the set of 2 by 2 square matrices with real number elements. I have a couple of examples here. I have a matrix 5, 0, 0, 5, and another matrix 0, 0, 0, 4. Well, we know that we would not consider these equal to 0. However, if we multiply them together, we do get the 0 matrix. So we would call these zero divisors. So zero divisors are elements in your set when multiplied equals 0, but they're not 0 themselves. So many sets do not have zero divisors, but here's an example of that. In this next section, we're going to discuss creating new rings from existing rings. We'll talk about subrings, extension rings, product rings, and quotient rings. Subring and extension ring are pretty intuitive. If you have a ring and a subset of that ring that is also a ring, we would call that a subring. In my example, if you consider the set of real numbers, which happens to be a ring, The integers is clearly a subset of the real numbers, and it's also a ring. So we would say that Z is a subring of R. The idea of extension ring is the polar opposite of that. If you just think about switching those two, since Z is a subring of R, then we would say R is an extension ring of Z. So you're beginning with a smaller ring and then, or with a set and then extending it to another set. So the set of integers is extended to the real numbers. In the product ring, we are combining two rings by element, and these are going to be ordered pairs, where the first element in the ordered pair is from the first ring. The second element in the ordered pair is from the second ring. And a product ring is going to follow these two rules here. If we're going to add two elements in this product ring, then for the first elements, we will use addition as defined by the first ring, and adding the second elements, we'll use addition as defined by the second ring. And then similarly for multiplication. And it might make more sense if we look at a specific example. I have two rings here in my example, Z2 and Z3. Now, Z sub 2 consists of the elements 0 and 1, and Z sub 3 consists of the elements 0, 1, and 2. So I have all the combinations of the ordered pairs, where the first elements are all from Z sub 2, and the second elements are all from Z sub 3. If I want to add a couple of elements, I've just randomly selected a couple, then I'll add the first elements, 1 plus 1, mod 2. So 1 plus 1 is 2. 2 mod 2 is 0. And when I add the second elements, 1 plus 2, I get 3. And 3 mod 3 is 0. So again, we use addition from the first ring for our first elements, and addition defined by our second ring for our second elements. And similarly for multiplication. 1 times 1 mod 2 is 1, and 1 times 2 mod 3 is 2. Next, we're going to look at a quotient ring, and it's going to begin with an ideal of our ring, which we discussed earlier. So the quotient ring is going to be the set, which we will notate as R/J, and it's going to consist of all the congruence classes modulo J in R. And again, we're using our binary operations. Addition and multiplication will be defined in this way. So x plus j plus y plus j is x plus y plus j. Similarly for multiplication, x plus j times y plus j is x times y plus j. If we think about this example, again, I'm using a simple ring, the set of integers, and a subset, the even integers, 2z, so z slash 2z, is a quotient ring. And it's defined with two elements only, 0 plus 2z and 1 plus 2z. Because 0 plus 2z will represent all even elements in our set, and 1 plus 2z represents all the odds. So I have an example of how addition would work in a quotient ring. 9 plus 2z and 3 plus 2z, just some random examples that I thought of, would be equal to 12 plus 2z. But remember, that is going to fall into our category of 0 plus 2z, since this is an even number. Multiplying gives us an odd number, 27, so that would equal 1 plus 2z. So you can think of quotient rings similar to cosets in groups. And that takes us to the next section. So we've looked at creating new rings. We're going to look next at ring functions. And we're going to highlight isomorphisms, automorphisms, and homomorphisms. And in this section, we'll also introduce the idea of kernel. Let's start with isomorphism. Here I have a function. All of these are functions from one ring to another ring. It's a bijection. So this means that we have the inverse property here. And it's an isomorphism if, first of all, it's a bijection and it satisfies these two equations. If we take two elements of our first ring and add them using addition as defined by the first ring and apply our function, it's going to be equivalent to applying the function to each element first and then adding with addition as defined by ring 2. Multiplication, similarly, if we want to multiply two elements in our first ring and then apply the phi function, it's equivalent to applying the function first and then using multiplication from ring 2. So we can say that ring 1 and ring 2 are isomorphic if there exists an isomorphism from one ring to the next. And I have an example. Let's look at the first ring as being the set of complex numbers, a plus bi. And the second ring will be the set of 2 by 2 matrices of this form. And so we can define a function phi from the set of complex numbers to this set simply by taking the real portion of our complex number and applying it here in the diagonal the down diagonal from left to right. And then the up diagonal from left to right, we will place the coefficient of our imaginary component here, negative b and b. So we can see that this function would work as also a bijection because we could simply reverse that process. If we wanted to add a couple of elements from ring 1, we would just get we would use complex number addition, and then we could apply the phi function and create this matrix. We would get the exact same thing if we first took each element of the two elements from our complex numbers, created the matrices, and then added. And so that's what we see here. It satisfies these functions, these equations for the isomorphism, because addition works whether you do addition from the first ring and then apply your function, or in the opposite order, applying addition from ring 2. An automorphism is a type of isomorphism where the domain and range are the same. In the previous example of an isomorphism, we had complex numbers as our domain, but we had matrices as our range. So if we want an automorphism, then here's an example. We have the set of complex numbers being mapped to their conjugates. And so clearly the domain and range would be the same. That's called an automorphism. Now, an automorphism is an isomorphism, which means it's still a bijection. We remove that requirement for a homomorphism. A homomorphism is an isomorphism without the bijection requirement. So an example of a homomorphism would be the set z sub 6 onto z sub 3 defined by f of x equals mod x comma 3. So this is a ring homomorphism. We're mapping all of the integers mod 6 to all of the integers mod 3. This is not a bijection because this is not a one-to-one function. There are more elements in the domain than there are in the range. So this would not be a bijection. Let's talk about kernel while we're here. If we have a ring homomorphism, as described above, then the set of all elements in our first ring that map to 0 in our second ring is called the kernel of our function, and it's notated capital K-E-R and then in parentheses our function name. In the example I've given above, 0, 3, the set containing 0, 3 is our kernel because F maps 0 and 3 in Z sub 6 to 0. F of 0 is equal to mod 0, 3, which is of course 0. And then F of 3 is mod 3, 3, which is also 0. So the function maps 0 and 3 to 0. So we would consider the set containing 0 and 3 the kernel of F. Before we move on, let's just review ring functions. Notice my large circle is homomorphisms. This contains functions from one ring to another ring. If we then require that function to be a bijection, notice the double arrow, then we're going to call that an isomorphism. And then a subset of isomorphisms would be our automorphisms, where the domain and range are the same ring. This is a visual about how those all are related. Finally, we're going to discuss ring classes. So rings can be integral domains, principal ideal domains, division rings, fields. Let's take a look at these meanings. First, let's talk about integral domain. This is going to be a ring that is commutative over multiplication and also has no zero divisors. So let's look at an example. We have a set of polynomials in two variables with real coefficients. And if you think about a polynomial with real coefficients, we can consider this to be commutative. Multiplying two polynomials, the order doesn't matter. So we would say this is a commutative ring. Also, if you multiply two polynomials in this set and your product is 0, that must mean that one of those polynomials is equal to 0. So we use that fact in algebra to find the roots many times. So since the product equaling 0 means that one of those is equal to 0, we would say that this set has no zero divisors. Remember, a zero divisor would give you a product of 0 without the element actually being equal to 0. So since this set has no zero divisors, other than 0 itself, of course, then we would say that this set is an integral domain. Again, the two requirements for an integral domain are commutativity of multiplication and no zero divisors. A principal ideal domain is a special kind of integral domain where all of the ideals are principal. Remember, we discussed that a principal ideal is one where the ideal is generated by a single element in the ring. So if we look at, again, we'll go back to our simple example of the set of integers. This is considered a principal ideal domain. First of all, it satisfies the properties of commutativity in multiplication. It has no zero divisors other than 0 itself. And also, the set of integers can be generated by a single element, 1. Let's talk about division ring. If you have a ring and every non-zero element of your ring has a multiplicative inverse in your ring, you call that a division ring. So if you add the requirement that every element other than zero has a multiplicative inverse, now you have a special type of ring called a division ring. A nice example of a division ring would be the set of quaternions. And this would be the polynomial a sub 0 plus a sub 1i plus a sub 2j plus a sub 3k, where your coefficients are all real numbers. And of course, I, j, and k are your satisfy the quaternion group properties. So this is not commutative. Notice that the division ring does not have the commutativity property requirement for multiplication. However, we can show that every element of the quaternions do have inverses, except for 0, of course. So we have a set. It is a ring. It is a non-commutative ring. And every element has a multiplicative inverse. And so we would call this a division ring. A special type of division ring that is commutative is called the field. So we have the properties of the division ring that also have commutativity of multiplication. So a good example would be the integers mod p, where p is a prime number. So the elements of z sub p clearly are a ring. They are satisfy the idea of division ring. We can show that there are multiplicative inverses in z sub p because p is a prime number. So we have a commutative ring. Every non-zero element has a multiplicative inverse in the group. So we call this a field. Here is a Venn diagram that fits together nicely the ring classes that we've discussed. So we can divide our rings into commutative and non-commutative rings. Notice that the division ring kind of hovers here on the border. Division rings can be commutative, as in the case of fields, or non-commutative. Principal ideal domains are commutative rings. And then integral domains are also commutative rings. So you can see how those fit together nicely. And that is it. Thank you so much for your time.